All right, hi everybody. How are we doing? How's day one? All right. All right, so in a few minutes, we're going to be having our plenary speaker, Dr. Warren Christensen, come up and talk to us. Before then, I have a couple announcements. The first is we got some feedback about if you're going to be speaking in the next 2 days. If you are a guest here at the Embassy Suites and you are logged on to the Embassy Suites guest Wi-Fi, for your talk, switch to the meeting Wi-Fi. Now, don't everybody switch, but if you switch to the meeting Wi-Fi, there's just fewer people on it and you have a better bandwidth, so you'll have less trouble. So for those of you that are giving talks on Friday and Saturday, when you go to give your talk, try to remember to switch to the meeting Wi-Fi if you're on the guest Wi-Fi. Now that we have done a day, and those of you that are virtual, I have put the direct links to the Zoom in the info document, way at the end. You have to scroll all the way down. So if you, I encourage you all to continue going together, but if you needed to directly go to a talk really fast, there's a slightly faster way. Breakfast reminder is breakfast is tomorrow, starting at 7 a.m. out here by the Starbucks. And if you are a guest of the Embassy Suites, you still have access to the Embassy Suites breakfast that has the omelets and pancakes. Tomorrow, dinner is not included in our registration fee. It's dinner on your own. There are a few groups who are organizing dinners. There are sign-up sheets out at the registration desk. So if you're interested in signing up and going out and having dinner with some people, maybe making new friends, you can add your name to that list. You can also just make your own. If there's anybody else who wants to make a reservation and make a list, you are free to do that, and I'll make an announcement about that tomorrow again. Today, after the plenary, there are a couple of activities that are going to be happening. So if you're interested in playing board games, there's going to be a few people, Katie Bjorkman, Franklin Yu, and Josiah Gomez. We all raise your hands so everyone can see who you are. So 1, 2 back there, and 3 over here. And they'll be out in the lobby area by the bar about 20 minutes after the plenary is over. If it gets too crowded there, they're going to move down to the breakfast area. So if you're interested in playing board games with some of the conference goers, meet them after the plenary. 20 minutes after the plenary in the circle of sofas, people will meet there and walk to Thunderhead Brewing, which is 3 blocks away. So if you're interested in going to a brewery, there'll be a group going there. You can also just go directly there. And that is all I have for announcements. So thank you very much, Jen Shoker. So I hear calls for Warren, but I'm sorry to say we're going to bring up Megan first. So introducing our plenary speaker is Dr. Megan Warrow.
Thank you. Thank you. Okay, I won't take up too much of your time. I've worked with Warren since 2013, so I think I got the baton this way. Where's the thank you. Okay, cool. All right, so you probably already know Warren is a physics education researcher at North Dakota State University, and he's been at RUME since 2010, which is a while. So I'm going to introduce him to you, meaning actually introduce you to him if you haven't known much about him. So let's see. Doing anything? What do I hit? The green? There we go. Okay. We are at the Red Star. This is the city of Omaha. You might not have known that Warren grew up at the Purple Star in southern Omaha. So he is from Omaha. While he was here, you probably didn't also know that he was part of a country western high school performing group. Let me zoom in for those for you in the back. Let me zoom in again. As Warren. Yeah. He was also part of the Ralston Community Theater. Here's another get up, and there he is in these two photos. Okay. Okay, so that experience put him on the path to fame. He's even been mistaken for some celebrities, like the Big Lebowski, the dude from Big Lebowski, Hulk Hogan, Thor, and Tom Selleck. Okay. On a more serious note, Warren is a lovely human. He is an excellent father to Andrew and Owen. So those are his two sons. And the one on the, whatever the side that is, the igloo, they live in Fargo. They actually like made that igloo together in their backyard, which is pretty cool. He's a very talented musician, and he's very committed to activism in his community in various capacities. So some things that are important to Warren. In terms of the music, you might have heard him at previous rooms and not known it. If you ever heard at a karaoke, Poor Unfortunate Soul from The Little Mermaid, that's a song. Yeah. But I want to close by bragging on him as an amazing colleague. You might know him from his personality. You can tell it's outgoing, but you should know him for his brilliance as a researcher as well. So my first interaction was this email that he sent to my advisor at the time, Chris Rasmussen. I guess I had just graduated. So that date is 2011. And he had said, oh, Chris and Michelle, my colleague and John Thompson and I attended one of your talks where you can read it there. Anyway, it was about linear algebra. And we thought maybe we'd ask our students in quantum mechanics. We think that might be interesting as well. And that kind of like made a big impact on my career and working with Warren as well. And so that led to all kinds of things. I think that's 2012. That's after a big grant was awarded in Pittsburgh in 2015. And we were working on this paper with Kevin there in 2020. And so working with him over the years has been great. I'm keeping it together. Okay, so that was start of an awesome collaboration. Like I said, he's been instrumental in my own trajectory for this math physics research. And I really don't think that grant would have succeeded without his input on how to make sense of students' understanding in quantum and how to kind of guide the questions and all that development. But in terms of other things as well, I think that's my last slide. Yeah. He's been instrumental in many ways of the discipline-based education research collaborations, also known as DBER, if you're not kind of in that area. So one of the big ways that I think set the stage was with Marcy Townsend, Chris Rasmussen, and John Thompson. They had 3 TRUCE conferences, and that stood for Transforming Research and Undergrad STEM Education. And so that brought together people in chem ed, physics ed, math ed, maybe engineering and bio as well, starting back in 2010. At RUME, we had the very first math physics, now math science working group in 2013, and Warren helped lead that very first one. And so, and he also runs a DBER RU and has students from all over the country learning about DBER research. And some of those students are here tonight, I think, right? There they are, good. So you can see his CV online. It'll show you that he's been NSF funded. He's published in his top journals like Physical Review, Physics Ed Research. And he is all but the very last checkbox away from being a full professor in physics at NDSU. That should be so cool. Yeah. Meaning just the Board of Visitors thing, the thing at the end. Okay, so hopefully this has helped show you that across his personal and professional life, he is dedicated to not just high quality research, but making everyone feel welcome, valued, and seen. So thank you for your time. How can I help? Give me your.
I'm gonna leave this up here. Okay. Yep, I got it. I'm not crying. The over under on Warren crying is at 3.5 now. So if you got your money in at above 2.5, you're in good shape. Yeah, not a problem. Thank you all so much. Okay, I think this is good. Right. So yeah, hi, I'm Warren. I want to start off by acknowledging a lot of the privileges that I have before I go into this talk. I identify as a straight, cisgendered, able-bodied white man. Both my parents went to college and graduated, so I am not a first generation. I don't know what that experience is like. I had a lot of support from them. I have an advanced degree in physics, and I'm here in part because my identity is highly privileged in our society, and especially in the discipline of physics. Physics has a lot of problems. It is racist and it is sexist, because you can see in the number of people that succeed in it, and that's not my fault, but it is my responsibility. And I take that line from David Kung, because at the 2017 Truce Conference, he said that, and I carry that with me all of the time, and try to share that with other people, and that's impacted other folks as well. So thank you, David, for that. He's here somewhere. Thanks, David. I wouldn't be here either without some pretty substantial funding from the National Science Foundation, so I want to acknowledge their contributions to the work that I've been doing. And as Megan mentioned, several of these grants are to run the discipline-based education research program in the research experience for undergraduates at NDSU for DBER things. And I just want to show you some of the folks here. We bring in 10 students each summer and run a program that across chemistry, physics, mathematics, psychology, and a whole bunch of other things. Like there's two individuals right here in front. They'll get shouted out here after a little bit. And this is a photo from 2016. And I don't know if you recognize, but there's two people right here. Let me zoom in on them. This is Dr. Kristen Amon and soon to be Dr. Sierra Street. If you both please stand and recognize. Which I just stop like, makes my heart so happy. Yeah, so that's pretty awesome just to be a part of amazing human beings like that. My goal here tonight, this is my goal, is I want to convince you that working between disciplines is crazy cool, that it is intellectually stimulating. It is wicked hard actually to do at the same time, but it's also like very, very rewarding. And that's the thing that I think more than anything else, that the reason why I'm here is because I love doing it, right? It's I don't know if I'm good at it or not, but I like it a lot. So to give you a sense of why it's difficult, I present of course, a Venn diagram that's going to have 4 quadrants, right? It turns out, so I'm going to be talking just about math and physics for a bit. We'll get into maybe some other areas a little bit later. But physicists have things that physics values, right? I mean, physics in general, there's things that physicists love about physics, right? I'm just say things and we'll just leave it general, right? There's stuff that we care about a lot. A lot of it is physics stuff, understanding physical systems, and mathematicians, most of which are you all in this room, have things that you care about as well. And sometimes those things overlap, right? We both care about integration. We both care about solving systems of equations, right? We might not do it the exact same way. We might not use the same notation. So there's still some disciplinary differences there, but there is some common ground. Now, what makes it really interesting, as most of you in the room probably know, is that not only am I a physicist, I'm a physics education researcher. And for those that haven't been around for a while or haven't looked across other disciplines, there's really interesting. So DBER as like an umbrella is really fascinating, but it has a lot of these like different pieces along with it. There's physics education research in undergraduate math education. There's biology education research, chemistry education research, all sorts of things that study teaching and learning at the university level, right? So there's things about PER. Each of those disciplines though has its own history. It has its seminal papers. It has its first people that were doing that. It didn't all come up together. It's kind of now getting connected later on. And so PER has its history and disciplinary norms, some of which overlaps with physics, but some of which kind of stand by itself. And similarly, you can imagine what the fourth circle here is going to be. This community has its history and its disciplinary norms that it kind of attaches to. And there are some areas that we want to like connect all these things together. And to be really successful at working within the bounds of math and physics, one of the places I love to play, it takes a lot of work. You have to negotiate so much stuff. There's so many different things. And so we're going to talk about that, like how I've tried to do that so far. So yeah, this is what the outline of this talk is going to look like, about discipline-based education research and me. I'm going to talk about my favorite theoretical framework, because this is RUME and y'all talk about theoretical frameworks, and that's one of the reasons I love this community so much, is because you talk about theoretical frameworks and mean it, and that's great. Not all the DBER folks do that across the board. I'm going to try to teach you something about non-Cartesian coordinates and unit vectors that you might not be familiar with, because I think it's fun. And then I'm going to talk about, this is one thing, this is like, feel a little bit shameful, but I'm going to talk about a really clever thing that I think I did one time, like a setup, a research thing that didn't really work. But like, I can't publish it, so now you have to hear about it anyway. Like, I want to get it out. So, and then looking ahead, we'll see if you want to have a romper at the end, right? So to give a little background, I got my PhD at Iowa State University, and this is my advisor, David Meltzer. David is an interesting fellow, an intimidating human. And I was there, and while I was there, I was studying, trying to identify student difficulties in thermodynamics, specifically entropy, calorimetry, and the second law. And we used a framework popularized by the University of Washington PER group, like Paula Heron's identifying student difficulties, where the framework was to look at the data and try to figure out what kind of difficulties students were having. And then you could use that to kind of create curriculum, right? It's a very historied tradition in PER. And we actually published some papers on this, right? 2009, 2011. But one thing that David also did not get tenure at Iowa State, right? Which speaks a little bit to some of the hardships that education researchers can go through when you're in a department that isn't friendly. And it's still to this day a very local problem that we all need to continue to keep talking about and understanding, and how do we work through that. But David did not receive tenure. He works now at Arizona State University. And yeah, so he left halfway through my PhD, which is not ideal, right? But what was weird is that I'm now in a department at Iowa State where there's 50 some odd physicists and me doing PER. And so I constantly had to battle. At the time, it wasn't particularly fun, but I think it kind of made me, I don't know, kind of street tough to talk to like physicists about PER, which isn't healthy, but it's a bug and a feature. Okay, like, so the outcome is good. Yeah, but so I was talking constantly to physics faculty, to graduate students that were outside of PER. And so I got to really listen, because I had no one else to support me. I had to really listen to what their condemnations of my field kind of was. And so that really got me thinking about what other things I want to extend, and where there are questions that aren't being answered sufficiently well, like maybe how do we do that a little bit. One thing that was nice, and this was my first kind of sweet taste of interdisciplinary things. Tom Greenbow was a chemist at Iowa State University, now at University of Oregon, just across the hall, basically, from the physics department. And because my advisor wasn't there, the closest like education research person I could talk to was a chemist, which is good because I was studying thermodynamics, which is kind of nice. But when you start talking to chemists about thermodynamics, you realize that chemists care a lot about enthalpy. Physicists don't really care that much about enthalpy, right? Physicists care a lot about work. We like doing work. Chemists don't really care about doing work. Chemists like to do things in like beakers that have no lid on it, right? So there's no work to be done. It just kind of flows away, which is why they care about enthalpy so much. I hope there's chemists. Where's Johnny? Is he right, Johnny? Is that true? Yeah. Fair enough, right? Some care about it, but most don't. And that's fine, right? But it was just like, oh, okay, that's cool. That's like trying to figure out those disciplinary norms, right? That wasn't a chemistry education research versus physics education research, but it was a chemistry versus physics kind of idea. So yeah, I learned about some of those, starting to learn about those things, right? And then I graduate and I go to the University of Maine, where I start working with John Thompson. And it was great. This is 2007, so I'm like going to things, and I happened to be in like the summer of 2008. Did we decide? There was this certain center at Maine was hosting this conference, and who shows up at the conference but Marcy Towns, a chemist. Right. And this is one of those serendipitous moments. I won't think I was like fully invited to this thing, but I happened to be sitting at a picnic table outside of the main conference center talking to John and Marcy. And Marcy and John were talking about maybe collaborating with this other math person named Chris Rasmussen about maybe having a conference with interdisciplinary like things going on, all these education research things. And I was also there, right? Because this is why, I mean, I know this is, you think I'm just diminishing myself, but it's literally like, oh, this badass in physics and in chemistry and in the math, and then me, who was just like a postdoc. But I got invited along, right? Like John's like, that's not true. And I'm like, it's fine. Even if it's not true, I think it's funny to say. So we actually wrote a grant and got funded to host TRUCE, as Megan mentioned, the Transforming Research in STEM Education. The biggest problem with this was whether we could make an acronym that had an acronym inside it. And we decided, yes, we could. This is TRUCE now, right? just jam stem inside there, no problem. I remember Chris seemed particularly dismayed about that, but we threw out a bunch of stuff. When you make an acronym, it's got to sound good and mean the thing, right? There'll be a recall, a callback to this, making the acronym later on in this talk. So we got funding for 2010, 2012, and then we got an additional grant to host it again in 2017. And the goal of Truce in the first two conferences was to bring education researchers from math, physics, and chemistry together and kind of negotiate those boundaries. And we also did biology in 2017, kind of added in another discipline, and that it becomes an issue of scale too. We haven't done one since because as you keep growing the number, people were like, well, hey, why is there no computer science education researchers here? And I am not one to build fences at all, but I also having quality conversations is hard when everybody is so all over the place in terms of content knowledge and their education research background, right? But it was very fascinating to watch these disciplines and these education researchers interact, right? As these things collided, there were some really funny conversations between Mike Klimkowski and Joe Reddish about why you need to teach evolution in a biology class. It was just fascinating stuff. And I think I'm going to channel a little bit of Walt Whitman here in the fact that in these situations, you should be curious, not judgmental. And what I'm really doing is not quoting Walt Whitman, because Walt Whitman didn't say this, but Ted Lasso did in the show. And in the show, Ted Lasso quotes Walt Whitman, but I found out in preparing this talk, because I'm like, this is a great thing. Plus, I've been just binging Ted Lasso for months because it's too good. It's just too damn good. But I think this holds true. Don't be judgmental. You have to go in. If you feel like you're being attacked because someone else values their discipline values a thing a certain way, it's not you. They're not trying to go after you. They're just trying to share their experience. And so if you're just curious and kind of really listen, you can get somewhere really cool. There's a wonderful vulnerability about not having to not being responsible for even knowing what the content is, because you can engage. One of the great things about these conversations is it was about the methods, right? It was about the analysis. It wasn't about phylogenetic trees, or it wasn't about weird content stuff that you don't need to know about. And there's something just brilliant and simple about that. And I love it. Plus, I love Ted Lasso so much. Okay. Hey, okay, sorry. Cheers, that's it. So Megan already introduced me, so now I get to introduce her back a little bit. Megan Waro is a colleague and a friend. There have been times before Zoom calls were a thing. Megan and I would have oh, you want to hang out and talk, and we would get on Skype and drink wine sometimes and just talk about academic life as we're trying to get tenure and all this stuff. But we actually first met in Portland at a RUME conference. It was fantastic because I was sitting at a bar and this person slides up next to me and says, quote, "You and I know some of the same people. I think that means we might be friends too." And I'm like, well, that's as good. That makes sense to me, right? It's the zeroth law of thermodynamics, right? A equals B equals C. But at that time, Megan had just graduated, I think, or was very near to it. And I was a first, second year faculty member. And one of the weird things that I want to convey is that I realize, for those that don't know me that well, that I may seem like an important person because I'm standing up here, but I still feel like a grad student. My image of myself does not fit this in any way. But Megan and I have gone through this all together, right? I mean, and had that time where we were unsure and trying to go through things. And she and I have collaborated a ton, like she mentioned, with her career grant. We ran the first working group here at RUME on math and physics, and now math and sciences educators, right? So spread out because we're inclusive, which is good. But ran that. We ran that thing. We published some papers together. We'd probably publish more if I was a better writer. But it's been fantastic. And we've done so much things working between how to use the use of linear algebra, or students' understanding of eigentheory and things in quantum mechanics courses and all that interaction, which is awesome. And I'm not going to talk about any of that for the rest of the night, because I can only talk about a couple things. The goal is to talk about a few things, and I love Megan, and she knows that. If you want to hear about some of that stuff, you can hear Idris Malik's talk at 11:30 on Saturday. He was one of my RU students this past summer. He's fantastic. So you can hear about meta-representational competence, which is just a fun word to say. But Megan has been a huge mentor and friend for a long time. And the other two human beings in this room that have been absolutely paramount to my success are Mike Loverood and John Thompson. Yeah, clap. You can't. That was the crime. That wasn't a cry. You can't find you can't find two better people, right? There's so much stuff that I share with them. We talk about like really hard things, talking about the physics and the math of all this stuff and what these things mean. But I also like, they're my guides. Like, I struggle with stuff sometimes, you know, like everyone does. And so Mike and John helped me through so many things and are so always understanding and patient and ready for me. And I can't thank them enough. Thanks, guys. Okay, so now let's talk about some data, right? Let's talk about some research. Cool. So this is a fun question. So this is actually a physics question. So this is a PV diagram. We don't need to talk about exactly what that means. PV because there's pressure and volume, right? P and B, P for pressure, B for volume. I know mathematicians don't like other letters. That's fine. It's a disciplinary difference. It's fine. It doesn't mean you're wrong. It just means it's different. And so this was a question that my advisor, David Meltzer, asked calculus-based university physics students and used an identifying student difficulties framework. And he asked this question to a whole bunch of students. Is the work done by the gas in process number 1 greater than, less than, or equal to the work done by the gas in process number 2? Now, I don't expect you to care about what work is, so I provided an integral because I know you all love integrals, right? So work in physics is defined as the integral of the scalar product of F and dl, where F is the force and dl is the infinitesimal displacement, right? It's a little, because I'm a physicist, I will call it a little bit of displacement. I'm sorry if that offends your sensibilities, but that's a disciplinary difference, right? I'm not saying you're wrong. And so what's really cool is that you can do some things, right? There's actually a relation for these two quantities with two other quantities. You can actually multiply this term inside the integrand basically by area over area, right? Which is just multiplying by 1. And then you take the F over area, force over area gives you pressure, right? And then dl, you take a differential length, a little bit of length, and you multiply it by some fixed area. Well, that's a volume. It's a really small piece of volume, right? So then you get the integral of P dV, right? Just by multiplying and dividing by area. Everybody good? Fantastic. Great. Should have asked that earlier, I guess. Okay, so now you have all of the tools, I hope, that you need to get this question right. Even if you've never taken thermodynamics before, using your math, just think math, okay? The letters are barely even there. So we have pressure, P, vertical axis, volume on the bottom, work is the integral of P dV. So everybody, come up with your answer. 1, raise your hands in the air. 1 for greater than, 2 for less than, 3 for equals 2. Okay, everybody wait, think. Got it? Okay, go ahead and raise your hand. 1, 2, or 3. Nice and high though, so I can see. PFC 5 is not the answer, okay? Yeah, thanks, Jay. Okay, yes, good. It is 1. It is greater than, right? Because we can read the area under the curve, right? It's right there, PdV. That's fantastic, right? That's terrific. So David asked these questions of students, and about a quarter to a third of the students identified that the work was the same. And when asked for explanations, a lot of students said that it was independent of the path. And this is something that we talk about quite a bit. I'm not sure if that language is familiar to most mathematicians, but there are certain quantities, like if you asked what the change in volume was between these two processes, that is path independent because it's the same. It's the same. Your delta V is V final minus V initial. It depends on the final two states, but the work depends on the path, right? So this was David's results, published 2004. Nice work, David. So I get to Maine, and John and I are talking about all this stuff and talking about it with a number of other folks that were around. We had this question, and we're like, man, you know what? Like, what if this isn't really a physics difficulty? Because you notice on the previous slide, this is a work independent of path. This was, David Meltzer claimed that this was a physics difficulty that the students had, right? But hopefully you're thinking the same thing we were thinking like 14 years ago. And we wrote this question. And we thought, haha, we're going to write down this little picture and we're going to ask students what is the, we're going to ask them, it's like the integral I1 and I2 are going to be the integral of these two functions, f of y and g of y, and then say, you know, like which of these two integrals is bigger, right? Or are they the same? Because wouldn't it be neat if like a lot of them said like the same kind of things, or if it was like drastically different? Maybe the math wasn't the problem at all, but maybe it was, we didn't know. So we thought we would ask this question. And we went to, this would actually be, Megan's right, it was 2010, but we submitted it in 2009, and I put the wrong date on. Everything else is accurate though, I promise, just this year is wrong. But this was the first RUME conference, right? And this is like kind of weird for us. So I don't know if y'all know this, and I got confirmation from Natasha Spear, tomorrow night's speaker, that there weren't a lot of PER people just showing up at RUME and like giving talks and like interacting with folks. I didn't realize that, but like John and I just kind of walked in and we're like, oh, and kind of like trying to walk around and meet people, but didn't really know anybody. But we have, that's the other thing about John and Mike and I, is that we've come to this conference quite a lot in the last like 13 years. And because we love it, like y'all throw a really good conference. I absolutely mean that. You have no idea. The entire physics education research community, well, not all, but a good chunk of them really don't like me because I'm like, we need to make our conference like RUME, okay? Like, I'm not, John and Mike will not. Like, I did it a month ago in the winter APC meeting because I get annoyed. Anyway, so here we paired Meltzer's work question. This was in the paper. So this was in a RUME paper. You can go find this paper if you want to. We paired Meltzer's work question with an analogous, this is our language, that makes me a little sick to say it now, analogous math questions designed to elicit any underlying mathematical difficulties in this context. So John and I write this question, collect some data. We thought we had some interesting results. We go to RUME and we're like, ha, we got our physics question, our math question. And then this guy is sitting in the front row. So this individual hasn't been around in the last few years, but this collared individual is Joe Wagner, right? And John knew who this was, and he was like, that's Joe Wagner. I'm like, I don't know what that means. But we were sitting there, and Joe's kind of has his arms crossed and looking up, and it just kind of like, we're like 3 minutes into our little 15-minute preliminary presentation, and Joe just says, well, that's not a math question. This is Father Dr. Joe Wagner, by the way, right? So like, and I was really, like, what do you mean it's not a math question? Like, we wrote this question. And this was the first instance, the first time that I came up with this, and just for this talk, decided to name the Christensen axiom, theorem, lemma. I don't know what math terms are, right? So like, pick whichever one of these that you like the most. But this is the, I like lemma, even though Megan had to tell me that I spelled lemma wrong. She's like 1 L, 2 M's. I'm like, oh, damn it. All right. So a little less like lemma than I thought. But the conjecture of education research at the boundary of math and physics. And what is that conjecture? It's that physicists write bad math questions and mathematicians write bad physics questions. Okay? This is universally, I have not seen this disproved. Like even not, and I have and I have a lifetime of writing bad math questions. I can tell you that, right? Or at least a decade and a half of stuff. But this is, it's just, and I'm not angry about any of this, but it's true. It's like something we need to understand. If we're going to work at the boundary, we need to understand that this is a real issue and like, what are we going to do about it? We also wrote this question, and in that end up thing, a very nice little picture graphy thing that was supposed to be a math question. And I think this is a little bit more of a math question than the other one. Oh, I should have said there was some stuff, right? The things that Joe got on for in that picture, all sorts of stuff like, oh, your lines just stop at the point. Like that's not a function. They would go beyond, or like the A and B aren't on the horizontal axis, right? Like all these things. Natasha's like, yeah, we're now, why we put Z versus Y, I don't remember either, but we thought we were the corner, okay? I guarantee you this was several hours of input. There's a whole bunch of other interesting work that one of John's graduate students did afterwards, having new variations of that question as well. But just to show you some of the history, that there is crossover, and there are situations, right? So that was a question we wrote in 2009. This is a question that Lillian McDermott, or Trowbridge and McDermott, published in 1980. So those who don't know, Lillian McDermott is basically like the founder of physics education research, passed away just a few years ago, and an amazing influence on the entire field of PER. Like you really can't possibly escape it, nor would you really want to. But like wrote a picture like this. And here's an interesting picture from a math paper, right? From Monk 92 that cites the Trowbridge and McDermott paper. So it's not like talking to people across disciplinary lines is new, right? It's a thing, even though I would argue that's not a really good physics question, but like that's fine, right? I think that's just not a way a physicist would write it. You can tell that someone else wrote that question, right? So post Wagner Gate 2009, 2010, this is the years off this kind of screwy. So I know that Joe's a man of the cloth and has great influence, but if you knew anything about Fargo in 2009, you would know that there was a major event happening there. Does anyone remember? Everyone forgot for like 1 year that Fargo is the home of the wood chipper. Instead, they asked if I was buying a houseboat because it flooded. The Red River is this really weird river. Fargo is flat, North Dakota is flat, and this happened, right? They shut down the entire town for 2 weeks, and I barely got it took a long time for me to actually get my paperwork signed to get hired at North Dakota State University because this was happening, right? Just a joke. The whole thing, it was actually a really beautiful story because the entire town like shut down to like stop everybody. Like the kids of Fargo saved the town from the flood because everyone came in filled bags. It was actually really cool. So anyway, let's get into it. Yeah, I should have cut that slide. So let's investigate the boundary of math and physics with a particular example. So this is going to feature a number of folks. So this is Marlene Vega, was an RU student sent to us. It's from Cal State Fullerton, who had some tutorship from Mike Leverwood, which is why she ended up applying. She was in Fargo for a summer. A different summer, Chaley Dalton from Pomona came and worked with us on this project. Alton Bradley, also another RU student, came and worked on this project from Humboldt College, and then my graduate student Brian Farlow also is contributing in this over the course of many years. So what is that going to look like? Well, before we get into that, we got to talk about the theoretical framework. Right? We're going to talk about doing research. Let's talk about that sweet TF. So some of you might be. I know that some people in this room are familiar with resources and framing. Some of you may not. I really like it. It's kind of been my jam, and it's kind of an evolution for me from when I started off. Trying to identify student difficulties is a very different set of circumstances than doing this. So I'm going to kind of give you a short rundown of this. So basically, resources and framing is a toy model of student thinking based on knowledge in pieces, which maybe people are a bit more familiar with. That's Andy DeSessa. I have a very funny Andy DeSessa story later. It's too long to drop in the middle of a talk, but maybe. Anyway, so that's what it is, right? It's this toy model. And that may be something. I don't know if that's something that mathematicians talk about. Physicists love toy models, right? We love to make the spherical cow. We round things off because that way you can write down the math for it, right? Otherwise, like weird shapes are hard to write down mathematical things for. But resources are basically knowledge bits that a person has found useful in some previous situation, right? That's the definition I'm going to go for. This is kind of my definition, not straight out of the book. So here are some resources, right? Here's some represented by these 7 red circles. So these are ideas, resources that you have, something that you learned at some point that was useful and productive in some situation that you now carry with you and could be potentially called on, or actually not really called on, could be activated by a particular question and then could be productive or unproductive in that situation. So some resources are locally coherent and are connected to other resources, some more strongly than others, right? So like some things, sometimes in your brain, the way this model would work is that you think this thing, and like it's really easy to think of this other thing if it's really tightly connected, right? But maybe if it's not connected to this other 3 things, that's going to be something else entirely, right? It's something else, even though all of these resources might be productive for a particular problem, depending on how a person frames it, maybe you don't activate this set of 4 resources that are hanging out over here, and you activate these 3 instead for whatever reason, something that your brain does. So this whole idea of framing, your brain unconsciously frames a problem in a particular way. And it's basically your brain, without asking permission, basically asks the question of, goes back into its resources and says, hey, what's going on here? Like, how should I approach this problem? And what resources do I think would be good? So it's all happening in the background as you're like, okay, the PV diagram is, so this is all happening. And so it may activate resources that will be productive, it being your brain, may activate resources that will be productive for the given situation, or maybe they won't be productive, right? That sometimes they just aren't. And just because a resource isn't activated doesn't mean a person doesn't have that particular resource. So this kind of pushes back, instead of focusing on like, oh, this is this wrong thing that this person thinks. It's this person is thinking something interesting, and maybe it's not being productive. It's not just particularly productive here, right? It's productive somewhere else, and I like that, right? I like that a lot. So how do you go about identifying resources? So this is something methodologically that I think is kind of funny in our field, because I would claim that if you read enough, yes, I have my own pitcher of water. If you read enough about resources, or specifically, you read about people claiming to use resources in framing as a theoretical framework, there's quite a variety, I think, in the literature of what you find about the different grain sizes. And this is a discussion that we should be having. I hope to write a paper someday. We'll see if that ever comes to fruition about this exact thing. And I'm going to give you a couple of the extremes, right? So some of the things, come on, baby. There we go. So every resource, so you'll find individuals that they're like, oh, cool. So you're identifying resources. So what's the underlying P prim? And if you don't know, P prim stands for phenomenological primitive. And by the way, if you ever are worried, if you're ever back at your home bases and people are like, oh, you do education research, and you can bust out phenomenological and be like, look, let's all try to say it together, okay? On three. 1, 2, 3. Phenomenological. Practice it, okay? You got to come off smooth. You can't say phenomenological and be like, yes, because then they know that you don't really have a mastery of that term yet. Epistemological, also a banger, like if that's another one, if you want to sound cool. But the phenomenological primitive is this idea that getting down to things, that's the knowledge in pieces idea. Getting down to simple things like closer means stronger is a phenomenological primitive. And so if you have a model that, or have a framework that says every resource has a P prim or is a P prim, I have a problem with that. That's not the way I want to use it. I don't think it's as useful. I think there's more utility if we can expand that. At the same time, you can run into individuals who will claim like, well, we've identified a student resource that when a bulb is closer to a battery, it is brighter, which is a well-known student misconception about batteries and bulbs in PER. And no one who studies resource theory should ever like say, oh yeah, this is a resource. Like, no, this is actually a difficulty. But sometimes people like to use the words in different ways, right? So I just think some of the literature here is a bit cloudy and could use some clarification, and I hope to provide that someday. Okay, so that's the framework, right? We all good on that? Sweet, awesome, great. We're gonna do some math now, kind of. I think it's math. Maybe it's physics, I don't know, you can tell me. It's probably already not math because I have X hat up here and people probably want I hat. Who's in the X hat camp? I hat? Okay, but definitely 2 camps. Okay, my hat's at the table. Calm down. Okay, so the X hat, I'm going to claim, is a basis vector, which is often, I think, used more in calculus textbooks. Physicists often refer to it as a unit vector more commonly, but both are fine. That points in the direction of increasing X and has a magnitude of 1, okay? Hopefully everybody's good with that. So X hat or I hat, if you prefer, that's what defines a unit vector or a basis vector. So we're going to practice. Here is a question for you. Here is a spiral. It's going inward. Props to Mike Loverid for writing this question. Well, actually, you didn't write this question. You made the picture. You come back. Trust me. So we're going to consider the motion of a particle in a plane as it's shown as it spirals inward toward the origin. All right, everybody sees the arrows. Super cool. Awesome. For all of you right now, for point A, which is on the left-hand side, I want you to point in the direction of X hat. Okay, okay. So this is called formative assessment. We're going to go back and remember, class, X hat points in the direction of increasing X. Okay, and has a magnitude of 1. That part, increasing X. Let's go back. So everyone point in the direction of increasing X. That's X hat. That should be this way. Good, awesome, very good. That was way better, way better. Okay, what about for point B? Let's all point in the direction of X hat at point B. What's crazy about those 2 points? It's the same way, right? X hat doesn't care. It's not time invariant. It is time invariant. It's like, it's just classic. It just doesn't change. It doesn't care. They're at the same direction. That's really awesome, regardless of where it is. It's not time, spatially invariant. So yeah, that's good. Y'all did a great job. Congrats. Give yourselves a round of applause. That was awesome. So yeah, we like unit vectors in physics a lot because we deal with vector quantities quite a bit. I really wish this would advance more easily. Okay. So we can write unit vectors in terms of x hat, y hat, z hat, or I hat, j hat, k hat, if you prefer. You can also define, so something we care about in physics are position vectors, right? Position vectors you can write as r vector, right? Where this red arrow would be r vector that has a component, a magnitude of x pointing in the x hat direction, plus a magnitude of y in the y hat direction, plus the magnitude of z in the z hat direction, right? So that's what that thing is. That's how you would write that down. I think everybody's okay with that, I hope. And you can even talk, to get a little more physicsy, about velocity vectors, where you take the time derivative of this position vector, and that's how you would get a velocity vector. Okay, not a problem. But as you're all familiar, there are other coordinate systems that we can use, and physics, getting into that disciplinary, comfy space, cares a lot about other non-Cartesian coordinate systems. I'll call the x hat, y hat, z hat a Cartesian coordinate system, and a few of these things non-Cartesian. So that's the thing. So we have a polar coordinate system here. This is actually a polar coordinate graph. And we can talk about r hat and theta hat, which I'm guessing for most of you, that's a little bit of terminology you might not be as familiar with. And that's okay. It's safe space, right? We're here to learn. So that r vector in spherical coordinates, so we can write it in that position vector, r x hat plus y hat plus z hat. Or like, why don't we just write it in polar? And then all you need to write is r hat. The magnitude is r, that's the length of the red arrow that's not up there anymore. And then r hat, which is the unit vector that points in the direction of increasing r. Okay, so we're gonna come back to this question in just a second. So there's some other things about these quantities. Now, there's a lot of benefit, and physicists love working within a coordinate system, like not just doing the translation, but if you wanted to translate between Cartesian and polar, you would do this, right? The magnitude of r can be written as the square root of x squared plus y squared, and r hat can be written in terms of x hat and y hat. It's cosine theta x hat plus sine theta y hat. And if you want to do some like really fun like scalar product stuff, you can take the scalar product of r hat with itself, right? What happens when you do that? On the right-hand side, the x hat and the x hat will pair up and you get a cosine squared, and the x hats go away, and then the x hat, y hat terms are 0. And then you get y hat and y hat make 1, but you get sine squared. So you get cosine squared plus sine squared, and you get 1, which is the magnitude of what the magnitude of r hat should be, right? Isn't that neat? So much fun. Okay, so this is a spiral question that Mike Leverett actually wrote. Consider the motion of a particle in this plane towards the center, and ask the students to draw arrows on points A and B to indicate the direction of the polar coordinate vectors r hat and theta hat. All right, so we'll see how well we did. So I want you now to point in the direction of r hat at point A. R hat is increasing r. It's in the direction of increasing r. Okay, should be going this way. You go from the origin to point A. That's in the direction of increasing r. At that point is now that way. What about point B? It's down this way. So it was like this, and now it's like this. Okay, good. All right. What's weird about that? It changed. It's different, right? The direction of r hat changes depending on where you are, which is different from x hat. That is an issue. That is going to be a problem. So the great thing about this is that Mike collected a whole bunch of this data at Cal State Fullerton, and when Marlene came to work with me for our RU program, she brought all this data with, and she actually went through and analyzed a fair chunk of this stuff, right? Here's r hat, but spoiler, there's theta hat as well. That points in the direction of increasing theta. If you think of theta increasing, it increases as you go from x, like all the way over, just like in math, right? No big deal. So what Marlene did is try to kind of capture and categorize what these students were saying from written free responses, right? They were collected in a math methods course. And it was hard. She worked so hard, did such great work to try to capture this, but it was hard. Because it turns out this is we didn't realize it quite at the time, I don't think, just how difficult this concept really was. But it was really hard to dig in and really understand what the students were saying from these free responses. This was from her poster that she published at the end of the summer, and gave us some guidance of where to go in the next direction. So this also happened. So we had this question, and what's my favorite thing to do is to go to Calc 3 classes and ask questions. So I decided, I learned my lesson. I wasn't going to try to write a math question, right? I was just going to give them the same exact question that we had given our physics students, right? So, or that Mike had given his physics students. I hadn't given them to physics students yet, but I was curious what the math students would say. So we took this problem, gave it to the end of a Calc 3 course, asked them to draw the vectors. We changed it just a little bit to make it a little clear what the task was, so they're a little more accurate. We asked them to draw it like right on the graph. We thought that might be easier. And when we did this is what's, I love this moment. We were there in this Calc 3, and this gentleman who was teaching the course just said, they don't know how to do this. Like, and I'm like, what? And he's like, we didn't do this. And I'm like, oh, and we immediately had to decide, what do we do? Do we like give them a quick tutorial, like tell them what to do quick? And I'm like, let's just test the system as it is. We have this question, we have other data on it. Keep doing it again. Keep things the same when you can, and just kind of take that little bit of wiggle to see what's different. He was right, it turns out. Only 3 people in the class got a correct response. And this is, again, I am not making fun of the students. I'm making fun of myself because I'm an idiot because I asked a question that students didn't know the answer to. But we were curious. We're like, oh, is it just because he didn't teach this to his students? Or is it like just not ever taught? So what did we do? We decided to do a calculus textbook analysis, because why not? Let's find out. I was curious, like, oh, this is the little piece of information I want to find. How do I find that most easily? Well, I can find that in a textbook. Now, does this mean this is what faculty teach necessarily? No, they could teach other stuff, but it's a pretty good baseline to say the existence proof of like whether or not there are non-Cartesian unit vectors. So Chaley Dalton did this during her summer RU, and we got 7 calculus textbooks. We used the very critical measure of using the 7 most popular on Amazon, which I realize is a methodological, like, but you know, it's 7 textbooks. Give me a break. It's not like we missed everything along that way. We found that in a standard calculus textbook, on average, only 20% of the chapters in a calculus textbook have anything that's not Cartesian. Okay, which again, this is not to make fun or to deride anything. That's just the truth of what's in, that's the data, what the data say. And then we actually looked for those 20% of chapters that do have something in non-Cartesian anything. The vast majority of the problems, even in those chapters, were heavily Cartesian, like used Cartesian coordinates. There were a few that used a polar that Thomas actually was like the most common. They use polar. Very few use cylindrical or spherical coordinate systems, which is something we use a lot in physics. And there was these very few, almost none of a you decide. Like you're almost always told, use spherical coordinates to do this thing, which is fine. But in physics, we don't do that very often. A lot of times it's like, just do the thing and pick the most convenient one. And that's supposed to be part of the fun, I guess, but it's terrifying. And students don't have any practice with it, right? And I don't think most physicists really know that. So the other thing that was really like kind of blew us away was that there was no evidence in any of the calculus textbooks we looked at that featured non-Cartesian unit vectors. Just wasn't there. And so, yeah, no wonder no one got the question right. Like it's not in the book, right? It's not there to learn. And we were kind of blown away by that. And I thought this was like a fun instance of finding something. So, and you might ask, like, why do physicists care? So we're going to zoom back down into that bubble, wait, Venn diagram this way, where we talk about physicists caring about physics stuff. This is the inside cover of Griffith's E&M textbook, a canonical upper level undergraduate E&M textbook. And this is there, right? Which is it's a fun trick. Like if people are like, what do you do? And I'm like, I do physics. And you like look and they're like, they're just terrified. This is just like your standard gradient divergence curl, you know, Laplacian in spherical coordinates. And you can see there are unit vectors in spherical coordinates there, right? That's in our books. Physicists really do care about that. Doesn't mean the mathematicians should, but we as physicists need to understand that this is brand new and likely confusing, right? Very confusing. Yeah, it's just that whole thing is bonkers. I just look at the Laplacian. I've taught quantum mechanics a number of times, and you have to write the Laplacian in spherical coordinates on the board. It's like just a 3-minute process to get it right, and you're guaranteed to make like 3 mistakes. So what do students think about non-Cartesian unit vectors, right? This is where we're bringing our resources and framing theoretical framework to bear, because we wanted to identify those resources. We had, Marlene Vega had done this terrific job of looking at these free response data and trying to parse out what the students knew, and it wasn't clear, because it turns out, I think, that the content was too challenging them to write meaningfully about it. They'd never seen it before in a math class, so that's a really difficult thing to expect them to know a lot about. And so that's what we were trying to do, is we're trying to identify the nugget of something productive, right? And this is, again, my little kind of definition of what a resource I think should be, and what we ended up doing for this paper you'll see in a sec, is identifying something that we see as good or that was right somewhere else, right? So it's not the student saying, well, this is my resource. It's nothing like that. It's basically doing an interview, watching it, thinking about things they say, what they write down, their gestures, all of that stuff, and trying to find the nugget of something good that they're trying to put into this problem. And it may be working really well, or it may be not, but we're trying to find the thing that we can identify as the resource, right? The really good thing. And that's what I mean for a resource to be, which I think falls between the chasm of PPRIM and something else. Yeah, so this is, like I said, it's not what the student thinks, it's our expert identification. So the student could be thinking all these other things, but I still think this is a productive way of getting at some stuff. So we conducted one-on-one semi-structured interviews. These were not like math questions, even though like we can argue, right? Is this a math question? If we're asking about R hat and theta hat, I would say, hell no, because it's not in the book, right? I mean, if it's not in the book, I don't think that makes it a math question, even though there was not really any expert physics knowledge required for this, right? We're asking about position vectors and maybe velocity, which is not high in the that's like chapter 1 of any physics book, right? So it's not like we're asking about really hard physics stuff at the same time. So we're trying to ask math questions in a physics way, right? That's what we're really doing. So that's what this question was. We did 8 interviews with upper division undergraduates and graduate students during this time. And it turns out we got a real rich data set. People said all sorts of stuff. And there was almost, at first, it didn't seem like anything was, I don't expect you to read that stuff. I see Michelle squinting her eyes. I'm like, no, you're not supposed to. It's supposed to show you that there's a cacophony of a whole bunch of stuff. Some of it looks kind of similar, but it all looks kind of different. Like nobody gave the same answer. But there was things that looked similar-ish. So what do we do with that, right? This is going to be a paper that we're going to publish here after a bit. But what did we do? So we did a thing that's very common in when using a resources and framing theoretical framework is we did a case study. We identified a student, Mark, and Mark was selected because he was particularly verbose and actively wrestled with his ideas he thought were conflicting or unsatisfactory. And through an iterative process that you can read about in the paper, because it would take too long to explain all of this stuff, we identified a bunch of resources that Mark had. And I just kind of throw this up because it would, again, take too long. I thought about trying to unpack all this. There's too much other stuff I want to try to talk about. So, but we did. It took a ton of work. Like, iterative is like funny. It was like constantly trying to drive in and be like, I just don't think that's it. I'm like, what if we called it this? And you'll notice that there's some P-prims, there are some resources like, R hat depends on X hat and Y hat. That ain't a P-prim, okay? That's not a phenomenological primitive in no way whatsoever. And you can't really do stuff like in the upper division, there's all these other tools. And Megan and I did something similar when we looked at students' ideas about eigentheory and stuff. We had to come up with like, is this a resource? Like, I don't know. But we identified a number of different resources, kind of put them in these different content areas, and then really looked at how he proceeded, how Mark kind of navigated through what things he thought of, when he thought of them, what things kind of connected and what didn't. It was really fun. And I think it's the best paper I've ever written. So if you want to check it out, please do. But I want to give you the opportunity, I can tell people are getting a little sleepy, to now talk and get excited because we're going to identify some resources together. Yay! So Mark, who's wicked smart, during this thing, during talking about all this stuff, at some point wrote this on the board. And it took an enormous amount of time for us to figure out what the hell Mark was doing. But I'm going to give you 1 minute to try to do the same thing, right? To see what you can come up with. So the goal, the task is, can you identify a nugget of what we might consider to be a correct idea, i.e. a resource, that an expert would identify that Mark is trying to use here that would be considered productive somewhere else? Go ahead and talk to your neighbors. Okay. Boy. Okay. That's all the time you get to have, because I've just been told that I'm going way too long. All right, so here's a hint of what we ended up coming up with, is that I think Mark is trying to do a combination of both of these things, right? He's relating R hat to X hat and Y hat, which is a very wise thing to do. There's a relationship for that, right? He doesn't have that particular relationship, but he knows that's something he needs to try to do. And also he knows of this other form that also exists, right? Isn't it cool? You like see this like of like blending of two really cool ideas together to write this thing that looks like nonsense, right? And I think about how many physics faculty would be like, oh my gosh, an idiot, right? Just like passing over it because it doesn't see the good stuff that's really there. So that's a really neat thing. The other things that we try to do now, having identified all of Mark's productive, or not necessarily productive, but all of his resources, we can go back now to our larger data set and kind of work at trying to identify where do we see these kinds of things now in the data. It's a little bit easier now that we have a really well-defined resource, many of them. We can see that now in some of the other data, which is like really productive. And something that I don't think gets done enough in resources in framing kind of literature. People tend to do the case study and then it kind of goes away, which is fine, but like we want to kind of go beyond that. And then of course, because it's the only thing I know how to do, we also asked some students at the end of Calc 3 some better questions that we thought we would be more successful at, and are trying to actually identify those, kind of see if we can actually find some of these resources in the written data, which is pretty cool. So how does one do research at the math physics boundary really well? Well, here's this like a shift, right? So that's it, bow, done with that. So one of the things I'm going to give you an example of is something that I think is really cool. You rely on the universe first to bring you an incredible mathematician. And then when you get this incredible mathematician, you go into the RUME literature and you're like, hey, I want to do some stuff with integration. And you find a paper by Stephen Jones, right? And investigating integration with math, and let's just call them physics questions, okay? That were written by a mathematician. Sorry, there's Stephen Jones, in case you don't know what his sweet little face looks like. And then you talk to the paper's author, and he's like, "Oh my gosh, yeah, Warren, that'd be great." And then you talk to Stephen, and you get into some of the details of like what he was doing with his work, and then you do some interviews, attempt some replication interviews. That's one thing that I'm usually pretty solid at. There's a lot of instances in doing research where I'm like, "Nope, I'm not going to change a damn thing about this. This is a mathematician wrote this. It's perfect just the way it is." Even though I would not write the question that way, it's the math, right? It's a math question. So we did that. Realized yet again that maybe mathematicians don't write very good physics problems. Which they aren't. Stephen knows this. It's fine. This is like perfectly. I am criticizing Stephen's abilities to write physics problems because he's a mathematician. Like that's not his fault. It's the Christensen conjecture, right? That it prevents him from doing so. So we wrote some of our. We want to do some more interviews. We kept the math questions. Stephen's very good math questions. And then wrote some physics questions that we thought a physicist would write, or at least I did because I wrote them. And then we conducted more interviews and just marveled at how the students like activate certain resources or don't in the different contexts. Things they would say during the math questions, showing that they knew how to do this thing, which somehow should be different or a little weird or when they did the physics stuff. And if you want to see more about this, you can go to Sam Giesi's poster at Saturday at 4:50. Awesome. So the clever thing, should I not do this? Oh, man. Okay, I'll do this. Yeah, I'll just skip this. So there's some cool stuff. Let's just say that I really don't like when people claim to have isomorphic questions that are never isomorphic for this exact reason. And so we tried to ask some questions, and this is my colleague Jennifer Momsen, who's, I could say volumes about her. She's been a rock for me at NDSU forever and ever in biology, and also crossing those disciplinaries. Things we asked this question, right? The math question from before, nice callback, and asked about math, a physics question and a biology question. But all of these things have the exact same language except the very specific language that it's in bold, right? Otherwise, the questions are identical. And we gave this to students in a college physics class and in a biology class, right? But we split it. We randomly gave half the students one question and half the students the other question, and then did that. And this is college physics and general biology. So in principle, these are a lot of the same students because biology students take college algebra, right? Or college physics. Well, I'm not going to give you time to talk about this, but what do you think it could reveal? And I'm going to go zing, zing, zing through all the stuff, the theoretical framework, the resources, and the framing, right? The goal of this, the thing that we thought would be so cool is, wouldn't it be neat, methodologically and theoretically awesome, if successful application of a mathematical concept like reading the slope, an instantaneous slope at a point, was strongly connected to the context of a question matching the course in which it was given, right? So the fact that they're in a biology class and they get a biology question, maybe that makes it a little easier to kind of get this question right. Wouldn't that be cool? You follow where I'm at least? I thought this was awesome, right? So this was my super cool thing. A whole bunch of people worked on this, 2 RU students, a postdoc, my colleague John, and it kind of had some effects. So you can kind of see some of those bars don't line up, right? Which is cool. Maybe there was something, but the signal was really kind of muddied, right? And I think the problem with that is that maybe it wasn't a biology question, right? this is really a physics question that I wrote. Now, I did work with Jenny Momsen, who's a biologist, and she's kind of like, yeah, that's fine, right? But it would have been very different if we started with a biology question and then kind of translated it into physics to try to make it match perfectly, right? So that was kind of cool. Thankfully, this amazing human, Dr. Tara Slominski, did the same kind of thing, but used blood in veins versus water in pipes to do something very similar, and had some really awesome results that you can read about. And also, this was part that first paper in 2020 was about interviewing physics faculty, A&P faculty, and engineering faculty, which is awesome. And the main reason I think that she ended up doing that is because in 2012, Keith Weber gave a talk at Truce talking about talking to faculty in terms of proof, which I don't know anything about proof whatsoever, but that was cool, right? That was a neat method, and that kind of influenced some of the stuff that Tara was actually working on. So this is gonna be like 3 more minutes. So what's to come? We started late, didn't we? Did we really? Thanks, Sam. So what's to come, right? So I want to wrap this up a little bit by talking like working in these spaces, like I mentioned, is challenging, but it's like incredibly rewarding. Like I love it, right? I absolutely love it. It does take dedicated folks who are willing to come to meetings regularly. So I think some of the success of this work is honestly, like I credit John and Mike like a lot in coming and to this conference, right? And talking to folks and mixing it up and Truce, and it's Marcy and it's Chris and it's everybody, right? Doing these kind of things, but that means a lot. That is hard to do. It's hard to get resources to do that. So I'm not saying that like you have to. I realize that I was really fortunate in a lot of ways to have the resources and the means to be able to do this. But currently there's a really high bar for access because you're trying to navigate all that stuff, right? If you have to know, you need to know all 4 things. You need to know something about all 4 parts to be able to really get into this stuff really well. And so there's a group of folks who've been working to maybe outline some bigger research questions at the boundary between RUME and PER to help other folks have easier access into it. That's who these individuals are, and there might be other individuals I'm missing, but these are folks who we've been talking together for a long time. If you've seen some of these folks aren't here, but it's very common that Michael Ortman will come over to Mike, John, and I and be like, tell me about quantum mechanics. And he just like wants to learn stuff. And so we're trying to work on this idea of creating something that we call, I like to call the Retreat on Mathematics and Physics Education Research, right? And acronyms are important. And so that's why we're hoping to throw a romper at some point. I've submitted this 3 times to NSF, okay? So like, it's not quite there yet, but romper's staying. I don't care. If it never gets funded, I'll die on this hill, okay? But yeah. Anyway, I hope that I did want to convince you that working between disciplinary boundaries is cool, it's stimulating, it's difficult, it's rewarding. And I hope that just encourage you to be a little more curious about that area if you haven't considered it before, right? Finally, with some acknowledgements, I'm going to thank all of the RUME conference organizers. I want to thank all of you for coming and attending and putting up with me for a little bit. I want to thank all my DBER collaborators at NDSU, and this is going to be a way cut down. I couldn't possibly fill enough pages. There's 2 people. All my collaborators, mentors, and friends, I'll kind of put that all in one big bunch. And I want to thank my mom. That's my mom. So thanks. So my mom passed away when I was 21. And like Megan said nice things, right? Like I like to think I'm a pretty kind guy. And all of me that is kind and caring is I owe to my mother. This is actually a bow tie that was made from a scarf that she wore. That's why I wanted to wear it today. And this goes back to that whole like feeling like a grad student thing. So I want to talk for a second just like to the grad students, because getting through grad school is hard. It's really hard. And I think people tend to know that, but I don't think we do enough to really help support and help people understand that. One last citation. So in my dissertation in 2007, I put this in the acknowledgements. And I wrote this. I'm not going to read it because I won't be able to say it, but maybe I can. I strive to embody the spirit of my mother every day. And I'm very glad to report that despite being put through the ringer of grad school, I think that spirit of fun and playfulness still exists in me. And I don't think that was that was something I was afraid I was going to lose. And so I don't want you to lose your humanity either. Like, I want you to care for yourselves. I want to take care of each other. Okay. Anyway, that's all I got to say. Thank you all so very much.
All right, so we have time for some questions. Can we cut the slides so we can see our virtual attendees in case they have questions as well? Couple questions. This is an incredible talk. There has to be a question.
Okay.
All right.
Yeah, I was just curious on the parts you were talking about where I see that a lot where we put knowledge in silos, right? And there's a good bit of research that says even the experts do that. And that's kind of what I was interested in is how, if you know of any of the work tying how students silo knowledge the way professionals do, right? Just because I'm an expert in mathematics doesn't necessarily make me good in physics.
Sure.
Right? Although I'm an applied mathematician, it's a skill I learned how to do a long time ago, right?
Okay.
But it takes a lot of work to do that.
Yep.
So I'm wondering if you know about some of the connections between that, if the same types of things that you see in experts do in siloing their knowledge that students do, and some of the similarities and differences between the two.
Can you repeat that last part? Just
Some similarities and differences between how experts silo their knowledge.
and how students do? Ooh,
Mm.
that's a really interesting question. I mean, the most evidence that I would have that, like, I think there are a lot of silos. So when I think about chemistry, thermodynamics, it happens. That's the thing I think of actually more so. You can find situations though. I mean, it's a very common thing to teach a calc-based physics course. Their students have had calculus, and you can give them like a task that I do like right away is give them the integral of a dt and say a is constant. Evaluate the integral, right? And all you need to do is say, well, it's a delta t basically, and that's it. But students are frozen and don't know what to do. And I'm like, okay, instead, write on the board the integral of 2 dx. And everyone's like, done, right? And I think that's an example of like they're just not, they know exactly how to do the task, right? But it's like that small subtle feature that changes. In thermodynamics, the same thing happens. We don't connect well enough, and students don't very often make those connections themselves because they see the thermodynamics of chemistry and the thermodynamics of physics and them being separate and being annoyed because they don't see enough of the differences. But that's also because we care and focus on different things. So I think there is definitely evidence of that kind of stuff that's happening. And the other part of stuff, and the thing that Joe talks about a lot, if you've seen Joe Wagner talk about transfer in pieces, like transfer is something, depending on how you define it, it happens never or it happens all the time, right? And so I think that on a macro level, the way we look at it large scale, I don't see that transfer happening all that often. It takes explicit intention to say, hey, remember this thing you learned over here? It looked like this, and now it's going to look a little bit different over here, right? I think that is. I don't mean to panic. Like, that's important. You need to do that because a lot of folks aren't going to do that, and then you lose some of our best and brightest because not because they don't understand the material, but they don't understand how it's connecting across things. Thank you. Yeah.
Hello.
Hi.
Yes. So I've noticed that a lot of my colleagues are in mathematical physics. They're very good at complex analysis. I mean, they've taken all these physics courses and they learn a lot of complex analysis through these physics courses. And
Sure.
I noticed that one of the questions you said during your talk that you gave them to upper level undergraduate students and some grad students.
Yes.
And you picked Mark from there, the case study.
Yep.
And I was wondering if you saw anything from those upper level students that had taken maybe complex analysis, if there was a difference, because I feel like these kind of questions, as a mathematician, we see this more in like complex analysis courses, which most STEM undergrad students don't have to take complex analysis.
Right.
They get to differential equations, we're done. Right. So I was wondering if there's anything that you saw there.
So it would be very interesting to look and parse apart like what courses they had, because a lot of our majors, upper division undergraduate physics majors are double majoring in math and physics. So they may have taken complex analysis. I don't know that, but that would be very interesting to see if they were more successful. I can tell you, I've never taken complex analysis, so hard time parsing off exactly what that might look like, but it is definitely something that we could look to see, like demographically, like what kind of other courses they had. Yeah, Jose. We got to have the Zooms.
Oh yeah, and I was thinking, and you were mentioning that you did like this review of calculus books, and I was thinking, okay, what if there's a review of complex analysis books, and maybe undergraduate level complex analysis books, and see
What would you want to look for in them? Like, again, I don't know what's in a complex analysis book. So like, what kind of things like, what would you look for?
Maybe like tackling these ideas of, dealing with unit vectors, complex vectors, like all these different things, all these representations.
Oh, okay.
And what their meaning is, okay, what does this mean?
Sure.
The rotations.
Yeah. Yeah, we didn't do a full review. I mean, we went in hard to look for this very specific thing, and even that took a long time to do. But I think it's a cool thing, honestly. If you're looking for ideas of like things to do, I think like looking at what's in the textbook is a perfectly like good thing. Like we can say that, oh, we value this or we don't value this or whatever, but looking at the number of instances of a thing in a book, or whether it's not there at all, is a pretty powerful thing, and that's pretty easy, right? You don't have to collect student data for that. That's just sitting around. Collecting student data is hard. Like, I love doing it, right? I love talking to students, but I'm just saying is like another little like, oh, hey, I think it's cool. I haven't seen a lot of other people do it either, and I just don't really understand why. Maybe they think it's boring, but I think it's cool.
All right, we have one more question, and then I believe there's going to be a finale.
Oh,
all right.
Sure, why not?
Okay, so pressure on the final question.
Okay.
I'm Sarah Castle. First of all, thank you for a great talk.
Oh, you're welcome.
So one of the things I was curious with is especially with thinking of the intersection of physics and math, with computation being viewed as like the third pillar of STEM now, does that change any of the ways, because of the ways in which mathematicians and physicists use it in different ways? Does that change any of the resources students would draw on, or anything about your thoughts on how this new tool that kind of almost adds like a fifth circle
Sure.
into your Venn diagram kind of mediates those interactions?
Wow, that's a great question. I'm certain that it does. I don't do enough like computational things, to be honest. So I wouldn't have the first idea about how mathematicians use computation to do various things. I have a slightly better idea of what physicists do. Yeah, I'm not really sure. I think that is definitely something that we should be doing more of and talking to our students. It'd be fascinating to look ahead to see how students navigate that space of using computation in mathematics and in physics. I can imagine maybe that might be more of a unified thing. Maybe there's more similarities in that area than there are on like how we write unit vectors or talk about integrals or infinitesimals or something. Yeah, thank you. That's awesome. Should I do the thing?
Yes.
I'm gonna do something a little weird, okay? So like, okay. So I'm gonna sing a song. All right. So this song's a little bit on the long side, so it's not like super quick, but it's an Irish song. I love it. And if you want to have a glass and raise it at the end, I will raise my glass. Otherwise, your arm will get tired. Okay. So just hold on. All right. Of all the money that ever I had, I spent it in good company, and all the harm that I done, lost it was to none but me. I went for want of wit. These memories now I can't recall. So fill to me the parting glass. Good night and just be with you all. The comments that I had, they're sorry for my going away. And all the sweethearts that ever I had wish me one more day to stay. And since it fell to my lot that I should rise and you should not, I'll gently rise and softly call good night and just be with you.
Let's thank Warren one more time. All right, so see you tomorrow. Have fun.